Voltage control of a single phase inverter. In many industrial applications, it is often required to control the output voltage of the inverter to cope up with the variation of DC input for voltage regulation for the constant voltage by frequency control. There are various techniques to vary the inverter gain. The most effective method of controlling the gain and output voltage is pulse width modulation control within the inverter. The commonly used techniques are single pulse width modulation, second multiple pulse width modulation is also known as uniform pulse width modulation, third one sinusoidal pulse width modulation, fourth one modified sinusoidal pulse width modulation, and finally phase displacement control. Let us see techniques one by one. So first we'll discuss about the single pulse width modulation. Single pulse width modulation. In single pulse width modulation control, there is only one pulse per half cycle and the width of the pulse is varied to control the inverter output voltage. The gating signal are generated by comparing a rectangular reference signal of amplitude AR with a triangular carrier wave of amplitude AC. Now this is our carrier wave and this is rectangular one is our reference wave. When you compare that, then this is the crossing point and this is the crossing point. So in between that there will be a gating signal for transistor Q1 between 0 and pi, and for negative Q4 will be triggered in the same way in between these 2 points. The carrier signal is less than the reference signal. The frequency of the reference signal determines the fundamental frequency of the output voltage. By varying AR from 0 to AC, the pulse width delta can be varied from 0 to 180 degrees. Now if you observe, if AR is at 0, then the pulse width of this signal delta will be 0. If AR is 0, delta will be 0. If AR equals to AC, the delta will be 0 to pi or 180 degrees. Now the ratio of AR to AC is the control variable and defined as the amplitude modulation index. M equals to AR divided by AC. Let it be question number 1. If this is pi by 2, then this value is pi by 2 minus delta by 2, and this is pi by 2 plus delta by 2. Then the output will be in between the conduction modes. This is our output V0. The output is in between pi minus delta by 2 and pi plus delta by 2. The RMS output voltage V0 equals to Q by 2 pi integral pi minus delta by 2 to pi plus delta by 2 Vs square d omega t under the square root. When you solve this, you are going to get Vs square root of delta by pi. Let it be question number 2. The Fourier series of the output voltage yields to V0 equals to sigma n 135 to infinity 4 Vs divided by n pi sine n delta divided by 2 sine n omega t. That is equation number 3. The harmonic profile with the variation of modulation index M, the dominant harmonic is the third harmonic and the distortion factor increases significantly at low power outputs.